Okay, let's talk a little bit about plastic deformation now that we have some crystal structure under our belts. So we know that atoms will move to new positions when you plastically deform it. So in fact, where did my paperclip go? There it is, right? If I take this little paperclip and I put it on too many pieces of paper and it deforms permanently, well, there's some elastic spring back like that, right? There's some elastic spring back. You can see it better on this camera. But then there's obviously some permanent deformation. And what's happened is at the atomic level inside, we've got planes of atoms starting to move past each other. So what I want to do is I'd like to cycle back and look again at our stress-strain curve for a typical metal. We knew looked something like this, okay, and see if we can define a few things a little bit more carefully. So, we certainly know that we've got the Young's modulus here. What I'd like to look at is when the deformation becomes permanent. And what we had said originally when we first looked at the tensile test is, well, probably somewhere close to the end of the straight line. Okay, so you remember here in this straight line region here, we said that stress is directly proportional to strain. It's directly proportional through this constant of proportionality, the Young's modulus. So when the line ceases to be straight, well, we could just call that the proportional limit, end of the straight line. But that's actually of very little practical use to us because, sure, if your professor draws a big orange dot on the line, well, it's clear where the end of the straight line is. But if you remember from the tensile test that we did, the end of the straight line is very difficult to determine exactly where it is. So it's not really very practical as a definition of plastic deformation. In fact, it's not entirely correct either because there's a little region here which I've identified, and I've actually exaggerated this. Okay, I should make a note of that. This is really not to scale. I've amplified it a little bit, considerably, but there is going to be some region after the proportional limit where you have what we would call nonlinear, but still elastic. So nonlinear elastic deformation. Okay, this region here, governed by Hooke's law, was both linear and elastic. So most materials, all materials will have a little bit of nonlinear elasticity. Metals, not very much, but a bit. And so if we want a thorough understanding of this plastic deformation, we need to appreciate that. It's still elastic. And then the other thing I wanted to discuss is what about the peak of the curve here? Well, the peak of the curve, we can go ahead and I'll give you the name for it. It's called the ultimate tensile strength. It goes by a few other names, sigma UTS, or sometimes just UTS, or sometimes sigma TS. So that's the peak of the curve, and I want to explore that actually in a little bit more detail. What happens right there? So, to do that, I've drawn in a little tensile specimen, okay? One of those specimens we put into the tensile test machine, and we stretch it out. Now, if I say identify this as the initial unloaded sample, what's going to happen when we when we put it under load? And what I'm going to try to do here, if this cooperates, is, okay, there we go, copied it out. And what I'm going to do is I'm going to just stretch it out a bit, okay? So we can describe a certain type of behavior here. This is, through this reduced section here, the elongation is distributed across that reduced section. So we call that uniform deformation. And say, if we want to be careful, we could say initially this is uniform elastic. So if I identify that as region 1, well, on this curve over here, region 1 would span from the start of this curve all the way to the end of the nonlinear elastic region, okay, where it starts to accumulate plastic deformation. All right, so that's fine. What if I continue to load beyond that? And so what I'm going to do is I'm going to put another sample over there, okay, and I'm going to stretch that. I'm going to stretch it even more. So now what I'm trying to describe is what's happening in this region here, okay? It's starting to plastically deform. It's permanently deforming, right? It's permanently changing. Oh, that fractured. That wasn't supposed to happen. The sample is permanently getting longer, okay? But it is still uniform. Uniform plastic. Okay, so I'll call that 2, and I'll identify that over here as 2. So then the big question still is, well, what's happening there at the peak of the curve? And so what happens at the peak of the curve is this. Okay, so I'm going to copy one of these samples here, and then I'm going to give myself a little bit extra space here to work with. So I'm going to actually copy that sample over to here, and then I'll try to replicate what we had done up to the UTS. So this sample has gotten significantly longer, right? You'll appreciate that. So this is at the UTS. But why does the engineering stress decrease after the UTS? And that's what I want to show you here by adding something to this. So somewhere inside the specimen, in the reduced section, you get a little localized deformation. The plastic deformation is no longer evenly distributed. Suddenly, in a small place, it gets smaller. Okay, and that might look a little bit like a neck, a neck of an animal or something like that, or of a human. I don't know. It doesn't really, but it's called a neck. That's actually what we describe. And so, at the UTS, we could say that we have the onset or the beginning of necking. And it's because of this sudden decrease in cross-sectional area gets very small, that we see the engineering stress decreasing. So the engineering stress decreases, and it decreases because the area gets so small here. But remember, this equation is sigma is equal to force over A naught. It's a constant. So really what we're observing is the force decreasing. The force decreases because the cross-sectional area gets so small. If I were to plot for you the so-called true stress, that is the stress that the material is actually experiencing, it would look something like this. But we're not going to explore that actually in this course, but that would be the stress that the material is actually experiencing in through there. And in fact, it's interesting to note that the metal actually continues to get stronger or to strengthen. Okay, even though we see this engineering stress decrease, that's only because the cross-sectional area has gotten so small there. So this, to finally just give you the last little bit of terminology, this type of deformation here, the necking, is referred to as localized plastic deformation. Localized plastic. Okay, great. Thanks a lot.